qui va nous parler de deep learning et de méthodes de graphes et leur utilisation en deep learning. Donc, on va avoir un exposé d'une petite heure et puis ensuite, on pourra passer aux questions. Alors, je ne sais pas si l'usage veut qu'on puisse interrompre ou pas pendant l'exposé d'intervenant. Je pense que oui. Donc, si Marc, tu es d'accord, on donnera la parole aux questions. Donc, on a tous l'habitude, je pense, maintenant avec Zoom. Donc, on propose de lever la main et puis on donnera la parole s'il y a des questions. And the talk will be in English.
Okay, thank you.
I guess.
Thank you, Stefan. I'm switching to English. So thank you for the presentation. So yes, please do not hesitate to ask any question during the talk. I will be talking about exploiting graph invariant in deep learning. So the topic I will discuss today is part of what people call geometric deep learning. So this is a survey which appeared a long time ago in the history, if you compare to the history of deep learning, so in 2017. It was written by Michael Bronstein, Joan Brunei, Yann Lequin, Arthur Slam, and Pierre van der Vis. And the main purpose of this survey article was to say that we can apply a deep learning technique to non-Euclidean data. So typically try to apply a deep learning technique outside computer vision or natural language processing or things like that, where the data has some structure, but which is not in a natural Euclidean space. So since this survey in 2016, there has been quite a lot of works on geometric deep learning. So there is now a website which is devoted to geometric deep learning. You see that Michael Bronstein is still there. He made a very nice keynote lecture at iClear last year. If you want to get a high-level view of geometric deep learning, I strongly encourage you to watch this video. And in my talk, I will focus on the general question of symmetries in machine learning and in deep learning. So the basic question I want to ask is what can be done if we are trying to learn a task or a function that is known to be invariant to some transformation. So we do not want to discover the symmetry in the problem. We know beforehand that there is a symmetry or strong invariant in the problem we are looking at. And we'd like to take advantage of this prior knowledge in designing a machine learning algorithm. So in order to introduce you to the main notion of this talk, I will start actually with a task in computer vision, because I think it's easier to present the notion of invariance and equivariance with pictures. So I will discuss a lot these two notions during my talk. So if it's not clear by the end of this slide, please ask a question for clarification. So what I mean by being invariant or equivariant, the first thing you need to consider is a set of transformation, which is denoted by S here, and which are basically, in this particular case, the set of translation. So you are translating the cat from this corner to the center of the image, and your algorithm, being a deep learning algorithm or any kind of algorithm, is your function f, and it's a classifier here, and it will be invariant if whenever you are translating the cat in the image, f will always give you the same prediction as the cat. So if you apply a transformation to the input, you want the output to remain the same if this transformation belongs to a particular group. So here's the group of translation. So this is the notion of invariance. For the notion of equivariance, let's consider a task which is perhaps a bit harder. So we need to decide to do segmentation, basically. So for each pixel, you need to decide whether it's a pixel belonging to the cat or not. So I'm considering the same set of transformation, namely translation of the cat. And now what I want is for each pixel to predict whether it belongs to the cat or not. So it does not belong to the cat if it's white, and it belongs to the cat if it's dark. And you see that here, if I'm translating a little bit the cat in the original image, in the input, I want, of course, that my map, sorry, at the end, to be translated with the same translation applied to the input. So equivariance, as opposed to invariance, I want when the input is translated, that's the output to be translated with the same translation. So these are the two notions I will discuss in this talk: invariance and equivariance with respect to a set of transformation. So in this case, particular set is.
Marc, this is Jean-Paul. It's okay if I ask questions?
Yes.
So what people now call equivariance used to be called in vision covariance in mathematics as well, I think, a long time ago.
Yeah.
But I'm sure you will address that problem, but to me it's important, but the key importance to me is not completely clear. And also there's this idea often in this kind of conversations that the transformations from groups, and at least in vision, they don't. In vision, if you take two pictures of the same object, they are not related by a true transformation because pieces will be missing, and they are definitely not related by a group of transformations.
Yes.
The difference will have between two images do not form a group. So will you address that? Or?
So yes, but well, not really. So here, when I'm saying a set of transformations, this is exactly because I didn't want to say a group. So it's more general than just a group. Yeah, and I agree with you that in computer vision, perhaps the group is not the most relevant structure you need to be invariant to. I'm not an expert in computer vision, so you probably know better than me. But when you will be dealing with graphs, you will see that the set of transformation is it's very different from this, and it's most of the time it's a group of permutation.
Sure, for graphs, sure, I
yeah.
believe.
So here I'm taking the computer vision aspect just to as you say, present the term, because equivariance was called covariance before, so I'm using the modern term, but to be.
I think in mathematics, the modern term is probably as much covariance as equivariance, at least, but maybe not.
Yes, but we are not doing mathematics anymore. So.
Oh yeah, yes, we are doing modern deep learning. Okay, I shut up. Thanks.
So you can replace equivariance by covariance if you prefer it time and saying equivariance. But I hope these two notions are clear. So to go in the opposite direction of what Jean just said, why is invariance or equivariance important? So here is one example where you take your favorite classifier for natural images. So everything after training, everything is behaving nicely, and what you do is you just translate a little bit your original image. So again, this is not another picture of the same object, but just a translation on the direction of the diagonal of the two images, and you hardly can see the difference on these two slides, but then you are making completely wrong classification prediction with exactly the same algorithm. So here, I'm only looking at inference time. So my network is already trained. And just by modifying a little bit the image, you see that it's not robust at all to this noise. Is there no? So the general motivation, so of course, this would not happen if you had an invariant architecture, because with respect to translation, because if you add invariance with respect to translation, you will output the same prediction, whatever the translation you are making on the original image. So this is one of the motivation to make your algorithm invariant. So the intuition is relatively simple. You will restrict the class of functions you are learning. Namely, in this case, you only consider functions which are invariant with respect to translation. So you will lower the complexity of your model, and if you lower the complexity of the model, you should naturally improve robustness and generalization. So the first thing you can say, there is a very easy way to transform an arbitrary function into an invariant version. This is just by taking the average over the set of transformation you want to be robust to. So again, here this big T is a set of all the transformations. So for example, small rotation or small translation. If you have on I, here is the original image. If instead of f of I, you will return this average over all the possible transformation, then for sure, this will give you an invariant version. So meaning if you translate a little bit the image, it will give you the same answer. So this is not what is done in practice, but what is done in practice is data augmentation, where you take your original image here and you do a small rotation or translation scaling of the image in order to learn now a function f, which will give you the same answer for all these images. So the intuition behind this data augmentation is that you want your function to be robust to this noise, meaning that whatever element of transformation you are applying here, you want to get the same label, the same prediction. So this is not an average like this. This is more an average done during the training, if you want. Now you can also take a more theoretical approach and try to construct layers which are equivariant. And there is a very nice mathematical theory behind this. So in this case, clearly what you want to detect the cars moving on the street or the pedestrian on the sidewalk. So you want when a car is translated in the image, so moving forward or something like that, you want to follow this car. So what you'd like is to have a kind of equivariant network. So again, as Jean said, this is an approximation, but equivariant to translation. So what you could ask is what kind of layer can you use if you want to have the output of the layer to be translated each time you translate the input. And it turns out that there is if you do the math, if you ask your layer to be invariant to translation, so I'm calling it a shift here. So if it's a shift equivariant, and if you are adding the constraint that the layer is linear, then there is only one solution possible for you. It's to use a convolution. So the convolution are exactly the set of all linear layers which are shift equivariant. So this is one justification, perhaps a posteriori, of why people are using a convolutional neural network. But then you might ask, okay, it doesn't seem to work since I have this problem with this was done with a convolutional neural network, and this is not shift invariant. The problem, one of the problems which is raised actually in the paper and solved in the paper I'm citing here, which appeared at ICML a few years ago, is that in convolutional neural network, you are also using other layers like max pooling. And max pooling layer will break the equivalence property. So there is no contradiction in what I just said. If you are stacking only convolutional layers, then for sure you will be shift invariant. But as soon as you are stacking max pooling layer, then you are breaking this equivalence property and you end up with the problem I just showed before. So now when you are trying to build invariant function like that, so there is a natural question which is coming at least on the theory side, which is, okay, I will stack convolution in order to be sure to be equivariant. But what kind of function can be approximated by my network? Since the general approach is I want to learn a task or a function that is invariant to some symmetry, I'm using layers that respect this symmetry. But then it's not a priori clear that I will be able to approximate any function that is invariant to some symmetry, to this symmetry. So, for example, for convolution to translation. So, for the particular case of convolution, there is a recent paper showing that actually by stacking, so again, this is a theoretical paper, by stacking only convolution, so on even more general maps, so invariant or equivariant map, you will be able to approximate any function that respects this symmetry. So of course, there is a well-known universality theorem of Simbenko and others saying that with a multi-layer perceptron, you can approximate any function. Here, you cannot approximate any function because you are building something which is symmetric with respect to some transformation. But what you can show in the particular case of convolution is that you can approximate all such functions which are invariant to this particular symmetry. So I don't want to speak too much about computer vision because, as I said, I'm more interested in graphs. But still, the notion that you need to remember for the rest of my talk is that we deal with symmetries in machine learning. The way I will deal with symmetries in machine learning are through invariance and equivariance. So I will try to build invariant on equivariant layer or invariant on equivariant neural network. For the particular case of translation, this invariance or equivariance, well, more precisely the equivariance with respect to translation, you end up with convolution if you look at linear layer. And using this equivariant layer for the particular case of CNN, you are not losing too much in terms of what I'm calling expressive power. So you can approximate any function that is symmetric with respect to translation. And as we saw in practice, architecture are not invariant, and you need to use other techniques like data augmentation or anti-aliasing in order to deal with this. So before jumping to the case of the graphs, I will consider another case with another set of transformation. And now I think Jean will be happy because this is really a group. So this is for a task when you are taking as input not only not an image anymore, sorry, but what is called a point cloud. So in 3D, so you have a set of points with the relative position in the 3D space. And I mean, you have basically the same task as with images. You want to do a classification, part segmentation, like here, the table with the top of the table, and so on, or semantic segmentation if you have a point cloud corresponding to a room with chairs, computers, and so on.
Mark, can I say one more thing?
Sure.
Even with point cloud, it's not a group because of occlusion.
Because of, yes, I agree with that. So I'll come to that. But at the end, you will agree with me, Jean, I'm sure.
I'm sure. With graphs, I'm sure we are.
But still, you agree that if you want to put a point cloud in your network, the order in which you are putting the points should not matter. Of course, other things will matter, like what you said, the position and so on. But here, for the sake of simplicity, I will only consider the ordering of the points. So the main problem I want to emphasize here is that if I'm giving you this table and starting with the point at the top and ending with the point at the bottom, I should get the same prediction than if I'm starting from the point at the bottom and going up, giving you all the points at the top. So this is exactly another notion of invariance or equivariance, but with respect now to a group, which is a symmetric group. If you are reordering the points in the point cloud, I want to get the same answer for the classification, or I want to get the same prediction point per point in the segmentation part. So here is the architecture of the Pointnet algorithm, and you don't need to understand everything. The invariant part is actually what is called the classification network here, which is in blue. And I want to emphasize a few things. First, n is the number of points, 3 is the dimension, the number of dimensions. So this is the input, your n points in dimension 3. And what is important in this classification network is, as you see, you are making transformation. So even this one and this one, which are completely independent point per point. Okay. So if you look at the paper, you are never mixing information from different points, except in this last max pooling layer, where you get what is called a global feature. So, but before that, you are applying exactly the same transformation to each point. From that, you obtain a global feature, and for the segmentation part, you are using this global feature in addition to the feature obtained point per point, okay, in order to get another score. So you don't need to worry about what these T-net are. I will consider a very abstract representation of my Pointnet network. So this picture above for the classification network correspond to basically this architecture where F is very complicated, but you are applying the same F to each point. So each x1, xn is a 3D point, and you are applying the same function F to each of these this point here. So clearly, this is an equivariant architecture, because if you permutate the order with the permutation sigma, so again, sigma, I will use it to denote a permutation of my original point, you will end up with the, sorry, I should have put a sigma of the Pointnet. But if you are making just a classification, you will just take a symmetric function of this function, the average, the max pooling, and the Pointnet will give you the right answer. But you see that this Pointnet architecture, so consider only this function. So it's mapping a vector in dimension n to another vector in dimension n, and you are only allowed to do things component-wise. It's not universal anymore, even in the set of equivariant functions. So a very simple example that you cannot approximate with Pointnet is just taking the average of both points and returning the average for both entries. So this is clearly an equivariant function. And it's not very hard to see that you cannot, for any function f you can consider here, you cannot compute this average because f can only look at x1 and x2 separately. And in order to, so if you want, so you see that this is a case where you are losing a lot in terms of expressive power by restricting your architecture. So the main point here is I want to try to recover as much expressiveness as possible, but still by remaining invariant to permutation. So one way to do that is actually what was done in an earlier paper, which is called deep set, and this is also done in the paper, and it's called Pointnet seg. So this is the second part here, the segmentation network here. Thanks to the global feature, you will recover the universal property you need for equivariant function. So namely now at a very abstract level, your new architecture is like that, taking as input n points, but now the function, the same function is applied at each point, but as also access to an average over all, so what is called the global feature over all the points here. So clearly, in this case, you can get the average of your points. Sorry, here, and I mean, indeed, you can show that any equivariant function can be written in this way. So this was done in the paper of Lipset. And okay, perhaps just to address the point of Jean that mentioned that this particular problem, the invariance to permutation is only part of the problem, but you have also you want to be invariant. For example, if you rotate your plane or stuff like that, you want to keep the same prediction, and this is taken care of in this as far as I can understand in this TNet architecture. And the TNet architecture was not used in the deep set algorithm. So this deep set algorithm should probably work with much lower performances for this classification on segmentation task with a larger point cloud. Okay, so I did cover the two main notions of invariance and equivariance. As you see, for the point cloud case, the group of transformation I'm interested in is it's really a combinatorial group. So this is a group of permutation, and which is closer to what I will be doing with graphs than the group of translation. So let's move on to graphs now, and just to make things a bit perhaps clearer on why invariance and equivariance is a key ingredient for dealing with graphs. Here is a very simple question. If you are asking for trying to do a linear regression, okay, so you have a noisy observation x and y, and you want to infer the beta. So a linear function of the y is a linear function of the x plus noise. But you know that your linear function is also invariant to permutation. So if you permutate all the entries, then you should obtain the same observation. Then just this very simple invariance to permutation implies that in your model, all the beta are exactly the same. So instead of n parameter you want to infer, where n is the dimension of x, you need to only infer one parameter. So this is what I was saying when I'm saying that these symmetries that are known a priori on your model will lower a lot the complexity of the model. So let's do the same thing, but now with a graph. So what is a graph for me? If I'm doing a linear function of a graph, I'm meaning a linear function of the adjacency matrix of the graph. So the adjacency matrix of a graph is just a symmetric matrix, if my graph is undirected, where I'm putting 0 or ones. I'm putting a 1 only if there is an edge between node I and node G. And now I'm saying this, I mean, two graphs will have can be the same, but do not have the same adjacency matrix. It's very simple. If you relabel, if you reorder the node by applying a permutation on the indices of your node, you will obtain a new adjacency matrix, but the underlying graph would be exactly the same. So now if I'm doing a linear regression on graphs, this means that I have a linear mapping of my graph to an observation. And if I'm permuting the nodes of my graphs, I should obtain the same label. So in this case, you can do the math, and it turns out that the set of all linear functions taking as input an adjacency matrix with this invariance to permutation of the row on columns, which is exactly the group I'm looking, the action of the symmetric group on the graphs I'm looking at. You can basically do only two things, namely sum all the coefficients on the diagonal, or sum all the coefficients which are not on the diagonal of the adjacency matrix. So in terms of graphs, what this means, this is typically 0 because on the diagonal you don't put any information. And this is basically the number of edges, total number of edges in your graph. So the only linear function of a graph will be to be able to compute the average degree or the number of edges in your graph. So again, you see that this is true whatever the size of the graph. So whatever the number of nodes, you have only two parameters to estimate now instead of potentially n squared. So again, the complexity of your linear map is much smaller than the original linear map, but you are losing a lot in terms of expressiveness.
Can I ask one more question?
Sure.
So are you interested in linear maps or affine maps? And does the fact of considering affine maps complicate things or not?
No, I'm not sure I understand why you're asking, but here this was just to give an example of the reduction in terms of number of parameters when you look at symmetries.
The reason I'm asking is that for most of the problems I know, it's not really linear maps you're interested in, it's affine one, so you have a constant. And I'm just curious. It may not be pertinent for graphs. I'm just curious whether it changes the problem or not.
No, it will not change here if you consider affine. But you will see we will consider we will not consider restrict ourselves to a linear map. So this was just to give you an example in terms of reduction of number of parameters. Does it answer your question?
Yeah. Just curiosity.
So, okay, to be a bit more formal, I wrote what is the problem with graphs is that there is no intrinsic notion of a representation of a graph. So here I have the picture of the same graph, G1 and G2, but they are not represented with the same layout. And you have the map here on the right, which tells you that actually this blue node corresponds to this blue node, and you can verify that it's connected to 3 different nodes, and the connection are exactly the same on the right and on the left. So again, the idea now will be to try to design a machine learning algorithm, and we do not want the result of the machine learning algorithm to depend on the particular representation of the input. So if I'm doing a classification of graphs, for example, I would like my algorithm to return the same result whether I'm entering the graph with this representation or the same graph, but with a different representation on the right here. So I will concentrate on invariant and equivariant GNN. So to make the notation clear, now I'm looking, the group of symmetry is a real group. This is a symmetric group, which is denoted Sn, where n will always be the number of nodes in my graph. I will always represent a graph basically as an adjacency matrix, but okay, you can put feature either on edges or on nodes. So this set of feature will be denoted by this F. So this is a graph is a matrix of size n by n with coefficient in F. And now the action of a permutation, so I need to define the action of the group on this tensor of order 2, and it's with this star operation, and this is exactly what you expect the star operation to be on a graph. You want to relabel the nodes, which means in terms of the matrix, you want to do the same permutation on the row and columns. Of course, permutation, you can also define an action of the permutation group on a vector of dimension n by just permuting the indices. And now two graphs are isomorphic, so they are basically the same. If you can go from one to the other with this action sigma, so if you can go from one adjacency matrix to the other by permuting row and columns. And the function I'm interested in are either invariant, meaning that if I'm permuting the row and column of the input, it will not change the output. So this is the invariant case. I'm also interested in the equivariant case. So this is typically a function f which take as input a graph, so a tensor of order 2, and will produce one feature per node. So in this case, what I want is if I'm permuting the nodes in the input graph, I want to obtain the same permutation on the output. So this is what is called equivariant now in my case. And with this notation of the star product, which is the action of the symmetric group on the tensor of order 2 or 1. Is there any question on this? So as I said before, I mean, if you want to make for any function taking a graph and producing, for example, a label in classification, if you want to make it invariant, it's very simple. You can take the average of this function over the symmetric group. The only problem is now you need to take the average on the symmetric group, and the symmetric group has size factorial n, so n factorial. Which is prohibitive as soon as n is bigger than 10 or something like that. So you will not be able to do the trick of the data augmentation, for example, and you really need to implement function f, which are built in as invariant or equivariant functions. So in doing so, we will see that you are losing a lot in terms of expressive power. So I will present first what people call the message passing GNN. So let me see. Which has the following form. So you have your graph with nodes, vertices on the edges. And what you do is you compute what I'm calling a hidden state at each node with the following recursive formula. So in order to compute at layer L+1 your new hidden state, you take a function of your hidden state at previous layer and the hidden state of all your neighbors. Okay, and now this function f needs to be symmetric, invariant with respect to the order of your neighbor here. So you see that here you have exactly the same problem as for the point cloud. We want a function f to be invariant with respect to the order of the neighbor. And we saw with deep sets or Pointnet sets that any such function can be written as a sum. So and this is a mathematical property here. If you want to make an equivariant, this is what I'm calling a message passing layer, because I'm passing the messages on the edges of the graph. In order to be equivariant, you can always consider function like this, where f0 and f1 can be chosen arbitrary, but are applied are the same for each node in your graph. So it doesn't tell you anything about how you will learn the f0 and the f1. It's only tell you what kind of architecture you can use in order to ensure that you will be equivariant at each layer. And if you are equivariant at each layer, then you can stack layer like that. You will remain equivariant. And at the end, you will obtain an equivariant graph neural network for the whole graph. So now, as we have seen, we are losing in terms of expressive power when we are restricting to functions. So here I'm not restricting to linear function, but I'm restricting to equivariant message passing layer. So I'm only allowed to pass messages along edges. And it turns out that the expressive power of such message passing algorithm, graph neural network is quite well understood. And it's connected to, perhaps I will go a bit fast on this. It's connected to the Weisfeiler-Lehmann test, which is an algorithm designed in theoretical computer science in order to study the graph isomorphism problem. So I will not describe the Weisfeiler-Lehmann test here, but what you can show is that your GNN will be able to separate, give different prediction for two graphs whenever this test is able to separate these two graphs, so to say that they are not isomorphic. This directly implies some bad consequences for GNN, namely if you consider deregular graphs, so graphs where every node has degree d, then it's known that the Weisfeiler-Lehmann test is useless, so you cannot distinguish any two deregular graphs. And here is another problematic pair. So you can show that message passing GNN, whatever the function f0 and f, so whatever the learning, will always give the same prediction for these two graphs, which are clearly not the same. So clearly, message passing GNN are not universal because they are not able to distinguish these two graphs, which are clearly different. So what we consider with Weiss-Azizan is a more expressive neural network, graph neural network that we call the Folklore graph neural network, because this is based on the Folklore version of the Weisfeiler-Lehmann test. And so you see that now you have a layer which is not taking as input hidden state on nodes, but hidden state on all pair of vertices. And you have a very nonlinear thing here because you have a multiplication here component-wise of the features that are coming from node I to K and from node K to G. So this is basically morally a matrix multiplication. So this can be done very efficiently. But it's completely symmetric in K. So what you can show is you still have messages, but now messages are going on all edges, but also on non-edges, so on all pair of vertices, as opposed to the message passing GNN before, where the messages were only transiting on edges. So if you are stacking layers like that, you obtain what we call a Folklore GNN. And it's very easy to show that this is still equivariant or invariant if you are aggregating the feature at the end. And so there are two main results dealing with this Folklore GNN. So as I said, it's equivalent, and it has the same power of separation. So it's as expressive as the Folklore Weisfeiler element test, which is strictly more expressive than the previous test. So with Weiss, as you know, what we proved is actually you can we characterize all the continuous function you can approximate with this graph neural network by deriving a Stone-Weierstrass theorem. And the result of Marron with Urs implies that this Folklore GNN have the best power of approximation among all architecture working with tensor of order 2 for the graph. So if you consider only a tensor of order 2, like adjacent symmetries of the graph, you have the best power of approximation among all the architecture which are known so far. So we try to, this is a theoretical result, and then we wanted to try to see whether it was working on a simple task. So we designed a task which is where the equivalence is crucial, and which is called the problem of alignment of graphs. The problem is the following: you start from graph 1 on the left here. You put indices on all the vertices, so 1, 2, 3, 4, 5, and so on. And now you add and remove a few edges on this left graph, and you remove all the indices on the node, and you will obtain the graph 2 on the right, which is basically the same one as this one, except the few perturbed added or removed edges. Now you do not have the labels anymore on the vertices on the right, and you try to match the label of this guy to which node it corresponds to in the original graphs. So here are the results obtained with FGNN. So in red, these are vertices for which we made a wrong prediction. So you see that when you have an isolated node, you are making sometimes error and sometimes you are lucky, but this is basically a random guessing. So here I'm plotting the edges of graph 2, and now I will not change the layout of the nodes, but I will put edges of graph 1. So you see that when I'm going to graph oscillating between the two graphs, I'm adding and removing a few edges. And again, the green vertices are the right prediction and the red one are the wrong prediction. So here you see that for what errors are made by my algorithm. So basically, I'm switching these two nodes and these two nodes between the two graphs, and I'm making here a cycle. So I'm predicting that this node is actually this one and this one and this one. So making a cycle like that. So how can you recover the original indices? It's basically by trying to recover the common edges in the two graphs. So here, this is what I have depicted. I'm plotting all the edges of the two graphs in only one representation, and the edges which are present in both graphs are in green. On the edges corresponding to noise, though present in only one graph, are in another color, orange or blue. So what your algorithm will try to do is try to recover all these green edges, and indeed this is exactly what happens. So here I'm plotting all the match edges which are recovered by my algorithm. Okay, so this is similar to the graph isomorphism problem, but in a noisy version. So how did we solve this algorithm? We use the Folklore GNN that I just presented to you, and this Siamese architecture. So the important thing to note here is that you have two branches, okay, taking graph G1 and G in the upper branch and G2 in the lower branch. You have a neural network here, the Folklore GNN, but they are the same here and here. So if you prefer, the weights are shared in the two branches. This GNN is building feature on the nodes of graph 1, building similarly features on the node of graph 2, and now taking the dot product between the feature in a graph 1 and in graph 2, I'm obtaining a similarity matrix between the two graphs. And from this similarity matrix, I'm able to find a matching between the nodes of G1 and G2. So here are the results, numerical results on synthetic data sets. So we compare with message passing GNN on other technique which have nothing to do with machine learning, or SDP or a spectral technique. And in red, you have the performance of our algorithm, which is over there. So this is the accuracy, so the higher the better. And you see in particular for regular graphs, so as I told you, for regular graphs, message passing GNN is useless. So here you might wonder how with message passing GNN they got a nice result. So they cheated a little bit by adding a local feature at each node by looking at the neighbor at depth 2 in your graph. So that with the noise you don't have a regular graph anymore. But still, the FGNN without any trick is still performing very well in this case, whereas the SDP problem is not doing well at all. These are for small graphs. On relatively sparse one, this is another comparison to another algorithm which is state-of-the-art for denser graphs. So again, this is accuracy plotted as the level of noise here. So when the noise is small, you are able to recover the accuracy is 1. And when the noise is increasing, your accuracy is decreasing. So this is the performance of our algorithm compared to grandpa algorithm, which is again a deterministic algorithm. This is not a learning algorithm. So a last thing I wanted to say before ending my talk is in this plot, you see that the performance is decreasing as the noise is increasing. But to obtain one dot here, what I'm doing is I'm training a graph neural network on a data set sampled at this level of noise. Now, to obtain this graph, what I'm doing is I'm training another neural network on another data set corresponding to this level of noise. And so each point corresponds to a different training.
Marc, we have a question from Mirko. He's asking why are the error bars so large for Nowak and co-authors?
So this is taken from their paper. You see that the number of nodes in the graph is relatively small. And so you have a huge variability, possible variability in the different graphs. And then, if I remember well, I mean the error bar obtained when you are doing the average on 1,000 samples per noise level. So I agree, this is much bigger. But I think, I mean, okay, here it's relatively small. In this case, it's much bigger, and I think it's due to the fact that message passing GNN are not working very well for regular graphs. So you have a lot of graphs for which you have a very low accuracy and sometimes a high one, close to 1.
All right.
So I mean, to get a lower error bar, you should probably look at larger graphs. So the last thing I wanted to say is this plot. So again, this is the accuracy. So the accuracy is when it's high, it's close to 1 here. It should be yellow or white, and when it's low, it should be dark. So what I'm doing here, let's consider a line. One line corresponds to one neural network trained at this level of noise. So this line, I'm plotting the accuracy of this particular neural network trained with a noise of 0.07, something like that. But then at inference time, I'm plotting the accuracy of this particular network for all the different levels of noise, which are written here. So both axes are correspond to noise. The y-axis corresponds to the noise at which the model was trained. On the x-axis corresponds the noise at inference time for a given model on an horizontal line. So you see that what we were expecting here is to get a good accuracy only on the diagonal. That will correspond to the case where your model was good only on a data set which is similar to the one you train your model on. But it turns out that it's relatively flat, actually, meaning that your network is generalizing very well across all the different levels of noise. So, for example, in this particular case, probably this model is the best among all the different models trained at all different noise levels. And so this is a great result in terms of generalization, because it means that as soon as the level of noise is not too small and not too large, you will end up with a model which will be successful in a wide range of noise at inference. So instead of needing to train one network for each of these points, indeed, what you can do is just train this network and apply it for all the different noise levels, and it will give you basically the same performance with a much lower training cost. So in a sense, you find an algorithm that is able to solve the noisy version of the graph alignment problem for a wide range of noise level, just with one training. Okay, I will end up with a last slide. So, what you should remember probably from my talk is you can deal with symmetries in machine learning thanks to the notion of invariance and equivariance. So to a set of transformation. So in the particular case of graphs, we are more interested in what I'm calling combinatorial invariants. And so the set of transformation you're interested in are typically groups, the group of permutation. So in particular, the group of permutation is huge when you have a decent graph. So meaning that you cannot use the trick of data augmentation in order to ensure that your network will respect will be invariant with respect to the permutation. So you need to hard code and to choose an architecture that respects this invariance. So we saw two different ways, which are practical in the sense that you can apply them to relatively large graphs. So the message passing one, and what we call the Folklore GNN architecture. And the Folklore GNN architecture is shown to be more expressive than the message passing one. So this is also a trade-off you need to keep in mind when you are dealing with symmetries. Basically, you are lowering the expressive power of your network. So sometimes, like for CNN, this is fine. You are still universal in the class of function you are trying to approximate. But for graphs, this is not true anymore. So you are not able to approximate any function you want of a graph if you are considering this message passing GNN or FGNN. And it's probably very hard to get an architecture that will be both practical and universal. There are theoretical architectures that are shown to be universal, but they are not practical in the sense that you need to take representation of the graph in much higher dimension, and you cannot learn anything with this architecture. So last point, we are looking at application of GNN, other applications, so in graph theory. So it has been used recently to find to disprove conjecture in graph theory, actually, to find counterexample to conjecture in graph theory. And we are looking at combinatorial optimization problem too, so where GNN are able to find good heuristics for combinatorial combinatorial optimization problem. And the last point related to the very famous transformers, which are, so I did not discuss them, but they are built on blocks which are equivariant. And the fun part is that with transformer, we do not want equivariant networks. Typically, they were introduced for NLP, where the order of the word in the sequence is very important. So in order to break the equivariance and to recover expressiveness, apparently, the author introduced the notion of positional encoding. So this is, I think, a new way of using invariance and equivariance. You start from an equivariant block, and then you improve the expressive power of your equivariant block by adding an extra feature, in this case, the positional encoding information. And that's it for tomorrow. Thank you for your attention. If you have any question.
Can I ask one more question?
Sure.
I'm sorry to be a pain, but so for point clouds, in general, it's not true that you use invariance to permutations, because point clouds are acquired by sensors, and sensors have structure. So if you take say a LiDAR, the LiDAR captures data more or less like a camera, because you have a horizontal structure, rotation, and vertical structure corresponding to the lasers. And there's no order, but it's not there is structure. There's not a predefined order, but there's structure. Likewise for transformers, it's not true that transformers lose if you apply transformers to images, for example, it's not true that they lose the image structure. The image structure is completely preserved, and you don't need the positional encoding to preserve that structure. People use positional encoding for reasons that I'm not sure exactly why. I think I have some ideas, but I'm not sure why. So what do you think this is? I understand again that you focus on graphs, and on graphs things are completely different. But this business of positional encoding and equivariance in things like point clouds and images for transformers, do you think those are key issues or not?
Okay, so let me start with an easy answer. For the transformers, what I had in mind is what people call the transformer block, which is basically you are stacking self-attention and then what they call the feed-forward network with layer norm and so on. And if you remove the positional encoding, this is completely equivariant. So meaning that if you permute it, the self-attention is completely equivariant. If you permutate the entry, you will permutate the output.
Yeah, but you don't lose at all the structure of the thing. You have a matrix that encodes the thing. You choose a particular order for your features in which you encode them, and the order is.
I agree with you, Jean. I mean, you are not losing the structure. In particular, the self-attention allows you to look at pairs of entries and to compute stuff corresponding to pairs of entries. So you are not losing the structure. The only thing I'm saying is it's a priori weird to build a block with such constraint, whereas this is not required for your task. I mean, you don't want in NLP, clearly the order of the words is important, and you don't want to lose this this order. You need more than just getting statistic on pair of words.
But you don't lose it.
If you remove the positional encoding, you are losing it.
No,
for sure.
No, you can recover the order of the things directly from the transformers completely.
Not with the transformer block. I mean, there is a proof for that. So if this is you are losing the order. I'm speaking about just one block.
Yeah, one block, one self-attention block, you don't lose the order. You have something that's equivariant, I agree, but you don't lose the order at all. It's still there. You choose the partial encoding of your data. It comes in the data and it's still there, and you can recover.
Yeah. Okay, I agree. So it's equivariant, meaning that if you permit the order of the input, you permit the output. This you agree.
Yeah, I totally agree, but it's not invariant, so that
yes. Okay. So it's invariant if you take a symmetric function of this feature, then it will be invariant.
And then you lose your structure. But
yes,
if you
exactly.
don't take a symmetric function, which mostly people don't do, then
I agree. So there are two. I mean, so if you take MLP on top of that, and if you add the positional encoding, then you are recovering. I agree with you. You are recovering the structure, the order. The question I'm asking is, why do you bother? I mean, building these equivariant blocks, whereas it doesn't seem to be required for your task.
Yeah, I don't know.
It seems to work pretty well.
Yeah. But... Okay. Just good. Thank you.
Okay, so we have a question from Elodie in the chat. How does this approach compares with the subgraph aggregation network from Bronstein?
You cannot compare it directly because Bronstein is using a subgraph, so it's not comparable in the sense you cannot, to the best of my knowledge, you can not show that his approach is better. I mean, his approach will be better for some graph, and this FGNN will be better for others. So there is no strict comparison possible unless you are taking a very large set of subgraphs in your original graphs. Indeed, in this case, but if you are considering a very large subgraph, then probably you can show that you are universal. But it's from a practical point of view, you cannot use this architecture anymore.
Any more questions? If not, I'm going to ask some stuff. So you discussed transformers, and so you have these very popular convolution layers and attention layers on graphs. And if I'm not mistaken, it's all message spacing blocks. And so what you say is that it's not a good idea to do that. You should do message spacing not on the blocks, but on the connections between the nodes. And
yeah, I'm not saying, okay, there is one part of the graph neural network literature I did not discuss here, which is more related to what you are calling, what people call graph convolutional network. So here, this approach is mainly posed by people doing signal processing, and they are looking at different problems. Typically, you have a signal sitting on a graph, and you want to do a classification of this signal, but the underlying graph is fixed. And in this case, it makes completely sense to try to, I mean, you can see an image as a signal on a graph where the graph is a grid. So each pixel, you have your 3-channel RGB, and you want to do classification or whatever. And then convolution are useful in this setting. So then the question is, if instead of a regular grid, you have a mesh or a graph which is irregular, can you extend the notion of convolution? And this is what they did. And I think is that in this setting, this is clearly.
So this is okay. So you mean that this is in cases where you have features attached to the nodes? And
yes,
you
exactly.
Want to,
but the underlying, so typically you have, I don't know, a maps or a road networks which is fixed, and then you have traffic which is varying in time, and you want to analyze the traffic, or you have temperature in sensors, but the sensors are fixed. So here I'm not considering this case. I'm considering different graphs at each time.
Okay, but you don't think that such layers, convolution, or attention blocks on graphs could be improved by looking at connections instead of nodes each time? You see, I don't know if I'm clear enough, but
So that's basically, I mean, okay, so there are networks which are called graph attention network, which are still message passing algorithm, but with with a self attention sitting on edges. So if in this case, it falls back in my message passing class. So you can show that for such graph, you have a limited expressive power. But what we instead did basically is to replace this self-attention on edges by a self-attention on all pair of graphs. So of course you are losing in terms of I mean, you need to make basically dense matrix multiplication, but you are gaining a lot in terms of expressive power.
All right. Okay, cool. Any more questions? I have maybe a last one. So you discussed data augmentation, and data augmentation is very useful in particular when you do unsupervised learning and you want to do contrastive learning or stuff like that. So it's very, very popular for image, for computer vision. You can train encoders without labels. And what about graphs? So do you think that something naive as removing, putting some noise and doing pairs and learning and trying to minimize the contrastive loss between two data augmented graphs, does it make sense to learn encoders of graphs or not?
Yes. So this is what we are looking at right now.
Oh, okay.
And there are already some results doing that. What would be nice in this direction is to do a pre-training for general graphs in order to do then, I don't know, classification or node embedding or stuff like that with a general pre-trained model. So what people did so far is probably what you had in mind, but by comparing the local neighborhood of each node. And what we are proposing is, instead of looking at the local neighborhoods, looking at the task of graph alignment directly in order to produce a nice feature on the node and to see whether it helps you for classification or stuff like that.
All right, cool. And the data augmentation is just about removing at random. This is
the question. So how much noise do you put in the data?
Yes.
Yeah, exactly. So this is what we are looking at.
All right, thanks very much. If there are no more questions, we will end there and see you next time. Bye-bye.
Goodbye.